Hello Year 11, and here we are at the last video for differentiation. And we are looking at differentiability today. Differentiability, the ability to differentiate a function, can't always be done. Now remember that the derivative produces a gradient function. It tells us the gradient of a tangent to the curve, to the function, at any point along that. Now, sometimes you can't draw a tangent. Okay, some things don't have tangents. And we're going to test to see how that works. Now, there are two broad conditions that have to be met. First of all, it has to be continuous, and we tested that in the last exercise. Right, there are three conditions for continuity. Right, the limit from below, the limit from above, and the function itself must all be equal at that point. So, my function must be continuous, and also it must be smooth. Right, we're going to look at this a bit more. The smoothness of a function at some point. We're going to test for smoothness by looking at the derivative of the function. The limit as x approaches the point from below and above, right, of the derivative. So here's an example, and there are a few steps. This will go for a little while. Now, first one, we're looking for differentiability at x equals 2. Here is a piecewise defined function, and to begin with, we're going to look for continuity. So, we look at what happens when I approach function x from below. Now, if I'm below or equal to 2, I use the top rule, x squared minus 2x. So 2 squared minus 2 times 2 is 0, that's fine. And what happens if I approach from above? So if x is greater than 2, I use this rule, 2x minus 1. So that's 2 times 2 minus 1, which is 3. So it's not continuous. Somehow this function manages to go from 0 to 3 in an infinitely small space. So, for that reason, it's not continuous and therefore not differentiable. And if we draw a sketch, and here's one I prepared earlier, if we draw a sketch, this is what it looks like. So, anywhere less than or equal to 2, I follow this rule here, which is a parabola x squared minus 2x with roots at 2 and the origin. So, we get that. But for everything greater than 2, I follow this rule, 2x minus 1, that is a straight line. And you can see, I cannot get from this part to this part without sort of jumping over this big white gap in between. So, that function is not continuous, therefore it is not differentiable. I can't tell you what the gradient is here because, well, there's a big hole there. Now, here is a different piecewise defined function. Similar, but different. So, first of all, we test for continuity by approaching the point from below, and I get 0. Approaching from above, right, 4 minus 2x, I get 0. That's great, and we try the value of the function as well. That should be equal to 0 for this to work. The function of 2 is equal to 0, so this function is continuous at x equals 2. That's a good start. Now we need to test for smoothness. So we differentiate the function. I differentiate the two parts there. So the derivative of x squared minus 2x is 2x minus 2. The derivative of 4 minus 2x is negative 2. So now my derivative is expressed as a piecewise defined function. Now, testing for smoothness, we look at what happens to the derivative on either side of that point. So if x equals 2, right, or just less than 2, it's 2x minus 2, which would be equal to 2. If x is just greater than 2, then I use the other rule, and that's just going to be equal to negative 2. That's a constant. And 2 is not equal to negative 2, so this function, while it is continuous at 2, it is not smooth at 2. Right, continuous but not smooth means it's not differentiable at x equals 2. And once again, here's a sketch. I'm in the road there, aren't I? Here we go, here's a sketch. So you can see continuous. I can trace that green line all in one smooth motion. However, what's the tangent at this point going to look like? Does it go across? Does it go up and down a bit like this? Right, because it's pointy like that. Right, it comes to a sharp point. That means my function is not differentiable at x equals 2 because it's not smooth, because the gradient changes so rapidly. Okay, there is another question here. Let's try this function, this piecewise defined function. So the limit, right, as we approach the point from below and above, I get 0 and 0, as well as the value of the function at that point is also 0, so my function is continuous. That's good. Now I need to test for smoothness, so I differentiate the functions. I get 2x minus 2, and here I just get 2. Now let's see what happens as I approach from below. I use the top rule there. So 2 times 2 minus 2, right, is equal to 2. And then we have a look at what happens if I approach from above. So this time we'll use the bottom rule there, and it's just a solid 2, a constant. So that shows that my function is both continuous and smooth at the point x equals 2. So that means that it is differentiable at that point. Right here, it's differentiable. Here's a sketch. Made it a little bit smaller this time. Now you see here, that part there is curved. That's my x squared minus 2x. Right, comes through there. And after that point, right, it continues smoothly along, but in a straight line after x equals 2 at a constant gradient of 2. Right here. So you can see there the graph of a function, a piecewise defined function, that is nonetheless smooth and continuous. Right, and that's when you need to test for differentiability. There are sort of 5 things that you've got to do, but 2 main things: smooth and continuous. Right here, continuous and smooth. That's it. That is differentiation for the time being. We will look at some more differentiation in some other topics over and over again, really, but that's it for the time being. If you have any questions about differentiability or anything else that we've covered in this topic, please don't just sit on those questions and stew on them. Please certainly try to solve them or look up the answers, but I'll be there in class. Make sure you ask me. Okay, see you then.